Okay. Yeah, welcome to today's colloquium. Our speaker is Sanu Bera from our Department of Mathematics of RKMVERI. He's a PhD student. And he will talk about polynomial identity algebras and representations.
Thank you for giving me an opportunity to talk in this colloquium. Today I will talk about polynomial identity algebra and its representation. There are mainly two parts of this my talk. In first part, I will recall some result on polynomial identity algebra, and in the polynomial identity algebra, and which will be applied in studying representation. Actually, in the second part, I will introduce two quantum algebra and apply this result of polynomial identity algebra on that, and try to classify simple modules on that algebra. Let's start with some definition. First, we will define polynomial identity algebra. Before that, all the algebra I will consider here will be associative unital algebra over the field K, and all polynomials will be uh, polynomials with non-commutative indeterminants. So any such polynomials f will be called a monic polynomial if at least one of the monomials in f with highest degree has coefficient 1. That is definition as monic polynomials as we know. Next, R satisfies f means if we replace all the indeterminant of f by the elements of R, then f will vanishes identically. Or in this case, we will call f is a polynomial. F is an polynomial identity for R. Next, a ring is called a polynomial identity ring if R satisfies such monic polynomial identity over Z. And sometimes we call origin polynomial identity algebra. Then if R satisfies some monic polynomial over the field K, and polynomials means here polynomials with non-commuting indeterminants, and minimal degree of a PI ring is actually the least degree monic polynomial that satisfies R, and this least degree polynomial is always exist actually. And here the definition of polynomial identity ring, one remark is no degree one polynomial can be an identity actually of any ring. Actually our ring is non-trivial, of course, so minimal degree possibility of minimal degree is at least 2 actually. So next, we will take some example. One obvious example is commutative rings. All the commutative rings that we have known previously, they are obviously polynomial identity rings. Satisfies a monic polynomial xy minus yx equals to 0. And this is actually least degree polynomial identity for commutative rings. Its minimal degree is 2. But in general, finding minimal degree is a difficult problem. We will show later how we'll compute minimal degree for general algebra. So polynomial identity algebra or polynomial identities has generalized the notion of commutativity actually here. And we will later see more examples. Some nilpotent rings also satisfies polynomial identity. Suppose nilpotent ring whose nilpotent index is n satisfies the identity x to the power n equals to 0. uh, for more interesting example, of course, we have to focus on matrix ring. That will be very obvious non-commutative ring and interesting also in the representation theory point of view. Another one example is exterior algebra on infinite dimensional vector space. It also satisfies an identity of that form. Here third bracket xy means actually additive commutator of x and y, means xy minus yx. uh, next the obvious non-trivial example, of course, this is 2 by 2 matrix over K. The ring of 2 by 2 matrix over K satisfies an identity like that, where bracket xy means additive commutator.
So, Sanu, you have not defined what is meant by this commutator symbol XY. You have not defined it.
Yes. I have not defined what I am saying. In example 4, I have defined what is the additive commutator means. Actually, sorry for that. For I have not defined in 3, but I have defined in 4 where the additive commutator means xy minus yx. And number 4 in that identity has special name that is called Hall's identity, and this is checked by easily because trace of that additive commutator is 0, and we can use Cayley-Hamilton theorem. That square of that matrix will be, of course, some scalar, that will be scalar matrix, of course, because that will satisfies its characteristics polynomial, so it will commute all any z another matrix. So uh, x y square z a commutator is 0 for 2 by 2 matrix ring, but of course not algebra or not all rings are polynomial
Actually,
identity ring.
4, you should explain a little bit more. Why 2 by 2 matrices satisfy this identity x, y
Because
minus x whole square is equal to 0? Little bit more explanation, perhaps.
yes, because any 2 by 2 matrix satisfies its characteristic polynomial. So here xy minus yx, that is a 2 by 2 matrix, xy minus yx, this is a 2 by 2 matrix. It satisfies this characteristic polynomial because it's trace 0, so its square will be some scalar time identity matrix, so it will commute
That is
any other.
that, that is what I'm. This statement you should explain a little more. That if trace is 0, so you have written trace is 0, then
Yeah, then the square will be a scalar matrix,
so
and
why? Why? I mean, if the trace is equal to 0, then why is it true that the square is a scalar matrix?
because of Cayley-Hamilton theorem actually, because of
So
that.
suppose that A is a matrix whose trace is 0, then how
Yeah,
can I use the Cayley-Hamilton theorem to show that the square of the matrix is a scalar matrix?
because this is we are considering only 2 by 2 matrices only, not general n by n matrices. So it satisfies its characteristic polynomial whose order is 2 actually. So its characteristic polynomial will be looks like x square minus trace of something and plus determinant, like that.
Mhm. Yes.
So
And
trace,
trace,
as trace is 0, so x square will be some scalar determinant actually. That is scalar actually.
x square will be the determinant. Oh, I see.
Yes,
Fine.
here x means actually bracket xy square.
Okay, that's fine.
Not all
That's what is
algebra are, of course, Oil algebra. Sorry. Not all not all rings or algebra are, of course, not polynomial identity. Here I introduce one example, that is Oil algebra, which is K algebra generated by x and y with a relation xy minus yx equals to 1. This algebra does not satisfy the polynomial identity if we take characteristics of the field is 0, but it always satisfies a polynomial identity if characteristic is positive. We will see later the more explanation of these two things. One basic thing is characteristics differ the center of that algebra. For characteristic 0, the center will be only k, and characteristic is positive, there is more element on the center actually. Next, I will discuss few properties of polynomial identity algebra, which help us to construct new algebra from older one, which will be a polynomial identity algebra. But a given algebra, it is polynomial identity or not, checking is very much non-trivial actually. So any subring on factoring of a polynomial identity rings or algebra is always a polynomial identity rings, and its minimal degree is of course less than equals to the minimal degree of the uh, whole rings actually. And any finite direct product of polynomial identity ring is also a polynomial identity ring. Another one is most interesting things, if we extend central localization, if we take a central localization with respect to a multiplicatively closed set, that will be also a polynomial identity ring if R is polynomial identity ring, and minimal degree will be same of R and RS inverse if S consists of regular elements. Next, one important things, R satisfies, suppose R satisfies a monic polynomial identity of degree D. then we can process of linearization, we can say that R always satisfies a monic multilinear identity of degree D. Multilinear means identity, if an identity is satisfied by R, all the variables are not linear actually, maybe some degree 2, degree 3 power will occur, but we can process of linearization, we can construct a new multilinear polynomial identity, but degree is at most D. Next, we will introduce another class of rings which will appears in literature lots of time, that will provides with our an example of an polynomial identity ring. A ring which is finitely generated as a module over its center, then it will be a polynomial identity ring. If it's generated by m elements over its center, so then R satisfies a standard polynomial identity Sn for all n greater than m. And this standard polynomial identity is actually defined here. This is actually multilinear and also alternating means if we replace xi by xj, then this Sn will be vanishes identically. So if we take Sm plus 1, then R actually satisfies Sm plus 1 because of multilinearity, and also it is finitely generated by m elements. This class of rings is very important actually, we will see later that will occurs in our case. In particular actually, for that take an example of finite dimensional algebra is also a polynomial identity algebra, because its dimension is finite over its center, and any n by n matrices over a commutative ring. If we take an n by n matrices, rings of n by n matrices over a commutative ring, then it is a finitely generated module over its center. It's generated by n square elements, so it satisfies the standard identity uh, Sn square plus 1, Sn square plus 2, and so on continuously. It will satisfy, at least satisfies Sn square plus 1. Now the question is, for that particular n by n matrices over a commutative ring, what can we say about its minimal degree? From that we can say that minimal degree is less than or equals to n square plus 1. Next we will see what is the exact value of its minimal degree, and the minimal degree is computed in this way. First we will show that matrix algebra over a commutative ring does not satisfy any identity of degree less than 2n. So next we will say more about that. First we will show that no monic polynomial of degree less than 2n is not satisfied by MNA. So here it is enough to consider only multilinear polynomial identity because of that R satisfies monic multilinear polynomial, then we can if monic polynomial, then we can change into a multilinear polynomial. So we consider f, which is just a multilinear polynomial of degree t, where t is actually less than or equals to 2n minus 1. And without loss of generality, we can assume that just coefficient of first x1, x2, and xt is 1 actually. But if 1 is occur another place, it will not no problem actually. Here we choose suitable r1, r2, rt in element or in a matrix algebra or matrix ring in such a way as that consider a sequence e11, e12, and in this way the sequence is actually take two elements in each row, e11, e12, two element each row except the last one. So here actually in this sequence 2n minus 1 elements. So in this sequence we can choose t elements sequentially, first t elements, then substitute in f for that r1, r2, and rt. Then f will actually r1, r2, and rt, and other sequence, other arrangement of r1, r2, rt will be 0, and this arrangement r1, r2, rt will be non-zero. In this way we can say that the matrix algebra does not satisfy any identity of degree less than 2n. But one celebrated theorem by Amitsur and Lebeditsky had proved that the matrix algebra, n by n matrix algebra over a commutative ring satisfies the standard identity of degree 2n. So from these two we can say that the minimal degree of matrix algebra over a commutative ring is 2n, because it satisfies the standard identity of degree 2n but does not satisfy the identity of degree less than 2n. And here one important thing is we have considered only matrix algebra over a commutative ring. So if we replace replace a commutative ring by a field, then same minimal degree will be 2n. Here one important observation is that for this algebra mnk, the k dimension is actually n square and minimal degree is 2n. There is a relation, k dimension is half square of the minimal degree by 2 whole square. That is one important observation. Later we will see this relation will occur more general algebra also. Now we will study the structure of an polynomial identity algebra. Mainly today's talk is related algebra related, not rings actually, but here we will see about the structure of a polynomial identity algebra, how looks like, and how can we say that it's polynomial identity, or what will be that minimal degree. That will be the our primary goal actually. First, central simple algebra. A central simple algebra is just algebra which is over its center, and whose center is actually exactly k, and it is as well as simple. Central simple by terminology central and simple. Its center is exactly k and it is as well as simple algebra. We also assume one things in this definition, which is in finite dimensional over k. But not all central simple algebra are finite dimensional. In literature we can say that Oil algebra characteristic 0 is central simple algebra but not finite dimensional. But uh, today's talk, all central simple algebra are finite dimensional. We have assumed that. Now we will compute the minimal degree, try to compute the minimal degree of this central simple algebra. So here we have assumed that finite dimensional condition that will help us. Central simple algebra is a polynomial identity algebra, and by structure theorem of Artin and Oedenberg, we can say that R is a complete matrix ring over a central division algebra. That is, R is isomorphic to MTD, where D is a finite dimensional central division algebra. And that is one important things, one important result of on division algebra. Dimension of a finite dimensional division algebra is always a perfect square, and any maximal subfield of H, divides the dimension into two equal parts of that central division algebra. That is, dimension of D over K is actually dimension of H over K square actually. And H divides D into two parts, two equal parts where dimension are same. And we if we extend the center of D to H, then that will be the complete matrix ring. That is actually M, the dimension H over K and H. That is complete matrix ring. This is central extension. And also this maximal subfield of D will also gives the structure. If we replace D by if we replace R is isomorphic to MTD, then we can write it actually MTK and tensor with D, and we have an expression D tensor H. So we can show that R tensor KH is actually isomorphic to MNH, matrix ring over H. Here H is actually field, that is maximal subfield of D. And from previous we can show that dimension is also here a perfect square actually. Dimension of a finite dimensional central simple algebra, that is also a perfect square. And and this relation we can say that minimal degree of R, here R is central simple algebra, is also 2n, because this is isomorphic to MNH. H is a field. So here minimal degree is of course 2n, because minimal degree of R and R tensor H is same, because R tensor H is central extension of R. So here for the case of central simple algebra, the dimension is a perfect square. We defined pi degree and another terminology, that is square root of the vector space dimension. that is actually n. Here square root of that vector space dimension, that is actually n, and this is always a perfect square. This is well defined, and obviously we have a relation that pi degree is actually minimal degree by 2, because here minimal degree is 2n and pi degree is n. So next we will consider another structure of another types of algebra. Actually first we will consider primitive, and next we will consider prime algebra, which satisfies polynomial identity. A ring is primitive ring if it suggests faithful simple modules. And primitive rings has a particularly nice structure by Kaplanski's theorem. Any primitive ring of minimal degree D, if primitive pi ring of course minimal degree D, then D is of course even, and R is actually finite dimensional central simple algebra, and its dimension is actually uh, depend on minimal degree actually. That's dimension is actually d by 2 square. And for the case of primitive pi ring, we can extend the definition of pi degree because it is isomorphic to a central simple algebra. That will be the square root of that dimension. That is means actually d by 2. Here minimal degree is d by 2 for primitive pi ring. That means minimal degree by 2 actually. And the generalization of Kaplanski's theorem for the prime pi rings is Poisson theorem. That is actually any prime pi ring is a central extension which is a central simple algebra. Suppose R be a prime pi ring with center Z, then the center is of course commutative domain. Then we can extend the non-zero central element. That will be Q is the just localization of uh, with respect to the Z minus 0, and actually F is actually the cosine field. That will of course a field, and because Z is a domain and S is actually just Z minus 0, and center of Q is actually F, because this S consists of regular elements only. So Q is central algebra over F. It is okay because F is also a field.
Oh,
To
why the center of Q is only F, not bigger
because
than F?
because S consists only regular elements. If S consists on regular elements, then center will be exactly same as uh, just ZS inverse, because Z will is the previously center of R.
No, that is correct. But I mean, what is the justification for this assertion that if S consists of regular elements, then it's
Because if it consists of regular elements, then but it can be proved that. But now I will go further, but later I will come back to the end of this talk. Okay. Uh, so Q is
oh,
an
yes. Please go ahead.
Q is an algebra which is central over F, and it is also simple. The simple is follows from the fact that any prime pi ring, if we take a non-zero ideal, this ideal also intersect its center non-trivially. So from this fact we can derive that Q is also a simple algebra. And we have already mentioned previously localization of a pi ring. Its pi degree is same is if the if S consists of regular elements, then the minimal degree will be same. Minimal degree of R and minimal degree of Q will be same as S consists of regular elements, and the dimension actually here follows from that actually minimal degree, because minimal degree is same from R and Q, and Q is central simple algebra. So its dimension will be a perfect square, and that is actually exactly d by 2, because its minimal degree is d. Minimal degree of R and minimal degree is Q is same. And from this point of view, we can extend the definition of pi degree for prime pi ring to pi degree of R equals to pi degree of Q. Just for prime pi ring R, we can define its pi degree as its central extension, that is central simple algebra. So by Poisson theorem, we can say that pi degree of R is actually half of minimal degree of R, because we have defined in terms of Q, but minimal degree of Q is same as minimal degree of R. Next, if R is a prime PI ring, we will see some consequence of Poisson theorem that R is actually prime Goldie ring because Q is in central simple algebra. Of course, finite dimensional central simple algebra, and whose complete ring of fraction coincides with actually
What is the definition
extent.
of a Goldie ring?
Goldie ring actually some ascending chain conditions on right annihilator, and it has a right module which has a finite rank actually like that. But there is some necessary and sufficient condition. This is that is called Goldis theorem, which gives us actually that prime pi ring actually is itself a Goldie ring actually, and of course prime Goldie ring, and whose complete ring of fraction is actually just inverting all regular elements actually, localization with respect to all regular elements, and that coincides with actually Q because it is Goldie ring. If R prime is a subring of factor is actually same as Q for prime pi ring, that is central simple algebra, which contains R, then R prime is also a prime pi ring. PI ring is easy, also prime ring is easy, just to localize that prime ring actually. And its PI degree will be same because this is a subring of an PI ring actually. R prime is a subring of an PI ring. Factor is also a PI ring. This is in central simple algebra. If R is an PI ring and prime PI ring, and if take any prime ideal, so PI degree of R mod P is less than equals to PI degree of R. Because of if we see the that part, the in definition of pi degree in terms of minimal degree, the minimal degree of R mod P is less than equals to minimal degree of R, so pi degree will be less than equals to. Now we focus on a special type of algebra and its structure, that is prime polynomial identity algebra with some restriction on it. This is affine and also um, over an algebraically closed field. And this particular algebra, Kaplan-Meier theorem, has an important consequence. Suppose we take a simple module over R, that is always exists. Take a simple module over R and quotient R by this annihilator of that simple module, that will be denoted as suppose R bar. R bar is actually primitive factor of that ring R, and Z bar will suppose the center of R bar. And of course, R bar is a primitive ring, just quotient by that annihilator. This is a primitive ring, and Z bar with the center of R. Kaplan-Meier theorem says that any primitive PI ring is central simple algebra, and center is Z bar. So Z bar is a field, and R bar is also central simple algebra. Of course, finite dimensional, or dimension is actually dimension of R bar over Z bar is actually square root of pi degree of R bar, because we have defined the for central simple algebra pi degree is actually square root of that dimension, and pi degree of R bar is less than pi degree of R, so we have that relation. Then by untitled lemma we can say that Z bar is an K affine algebra because Z bar is central and R bar is finite dimensional uh, algebra over Z bar. So Z bar is K affine algebra, and also by Hilbert-Nulst-Stollinger we can say that um, the dimension of Z bar is in field. So dimension of Z bar over K is finite, and since K is algebraically closed, so the center is actually exactly K, where K is an algebraically closed field. So here R bar, we have to take primitive factor that R dimension of R bar over K is
How,
actually
where are you applying the Hilbert-Nulst sats? You are saying that Z bar is affine, okay? And then you
no
are
no.
saying,
I have used to to claim Z bar is affine. We have used Artin Tatelema, but we have used Hilbert-Nulst to prove that this is finite dimensional,
you are
because Z
saying
bar is affine field, K affine field.
affine
So
algebra. No, no, affine algebraic. So Z bar is of course finitely generated over K, right? Means that Z
yes,
bar is affine over K. And then you are saying that the Z bar is a field, right?
Z bar is of course a field because
Field.
this
So
is
it's a
center.
finitely, so it's finitely generated over K.
Yes.
So finitely generated over K will mean that um, mm,
So this is one particular types of Hilbert-Nussdalen. It follows from Hilbert-Nussdalen.
but finitely generated field over Z, another field, I mean over the base field, that
Yeah.
means that it should be algebraic.
Yes, base field is algebraically closed field. K is algebraically closed field. That's why uh, Z bar will K actually finally. Because if we not assume algebraically closed field, we can say up to that this is finite dimensional Z bar over K.
No, no, I'm saying something different. I'm saying that Z bar is finitely generated over K, right? That
Hmm.
itself will it is finitely generated as a field. So, I mean, why will it? Because I am worrying about the assertion here that Z bar, the degree of Z bar over K is finite. Okay, I'm concerned about this, right?
Okay,
So,
we will talk about that later actually. But this is true actually.
okay,
Okay, we will prove that later actually. We can use actually Noether normalization lemma actually to prove that actually. K is field actually. So Z bar is also finite dimensional actually. Thus here R bar is an finite
no, no,
dimensional K.
I think the answer is that because R is finite dimensional over K, right?
Yes, yes,
Therefore, K is also finite dimensional. Okay,
yeah,
and K is also finite dimensional. Sorry, Z bar is also finite dimensional over K. Hmm?
yeah,
Because
yeah.
R bar is finite dimensional.
But
So
R bar is finite dimensional over Z bar, not K.
I see, I see.
But
Okay,
here actually explicitly use of actually one version of Hilbert-Nussdalen, that is Zariski lemma actually, that follows from that Zariski lemma. Explicitly that statement is explicitly same actually. Any affine K algebra which is field, that is finite dimensional.
affine K algebra, which is field, is finite.
Field, finite dimensional. That is one version of Hilbert-Nussdalen. So here actually R bar is finite dimensional over K and its dimension is bounded by actually pi degree of R square. And here we again use Artin-Weidenberg theorem that that R bar is primitive ring that is finite dimensional and central simple algebra, and here the center is actually K. So that will be the complete matrix ring, n by n matrix ring over K, and that n is actually bounded by pi degree of R because n square is actually dimension of R
So
bar over K.
you are trying to say that R bar over K is less than or equal to pi degree of R square. I mean the
Yes,
dimension.
yes, yes. Because if we see the number two, the that is finite dimensional. So dimension is actually bounded by pi degree of R square.
Oh, but you are saying that Z bar coincides with K.
Yes, that why
Okay.
the center is actually K. That why R bar over K is finite dimensional.
Okay. Okay. Fine.
Yes, yes.
You
So
found
that n is actually bounded by pi degree of R, and that will be important actually. Actually, in this consequence, we have proved that actually, if we take any
no, no, no,
primitive
just
factor.
please go back to the previous slide. You are saying that in this Artin-Weidenberg theorem, we conclude that R bar is equal to MNK.
Because that is finite dimensional central simple algebra over K. So that will be the matrix ring over some division ring, and of course finite dimensional division ring. So K is algebraically closed. So division ring will be K actually. So R bar will be the complete matrix ring
Hmm.
over K. Okay, and N is actually bounded by the pi degree.
Okay, fine.
Next, actually, we just restate that as a theorem that what we have proved that if R is an prime affine pi algebra over an algebraically closed field, then any primitive factor is complete matrix ring over that field K, and that T is actually bounded by pi degree. Here we have used T, the subscripts. And number two, if we take any simple modules over R, then the dimension of V is actually finite, and exactly dimension is T, where T is bounded by pi degree. Because if V is a simple R module, so R mod annihilator of V is an primitive ring, that will be the matrix ring. We have proved one, that will be the matrix ring, and any two simple modules over matrix ring are isomorphic. So here V is an one simple rings, and k to the power t is also a one simple ring over mtk actually. So V is of course infinite dimensional, and T is actually bounded by pi degree. So number two, we actually claim that any simple module over R is finite dimensional, and its dimension is bounded by pi degree of that ring. Here our assumption is R is prime affine pi algebra over an algebraically closed field. So the k dimension is bounded by its pi degree, and this upper bound is actually attained every times. I am not going to that exact that part actually, but that upper bound will attain. We will see later in example. In thus from that we can actually say that pi degree in terms of dimension of its simple module, just pi degree of R is just upper bound of that T actually. And this at this upper bound attained, so we can define pi degree in terms of in this way, that maximal dimension of its simple module. So pi degree of R, where R is an prime affine pi algebra, is actually maximal dimension of its simple modules. Next, we will define a presentation of an rings uh, which is a skew polynomial ring. Sometimes quantum algebra can be presented in this way actually, and this presentation will gives us lots of ring theoretic properties easily actually, whether it is Noetherian or not, or prime or not, easily. But in terms of generators, if we define an algebra from that, to say that it is prime or not, it is very difficult. So tau be an endomorphism of a ring, and a left tau derivation is an additive map that satisfies the product rule, like left tau derivation. So here is an twisted by tau actually, where tau is an endomorphism, and this pair tau and delta will be called skew derivation. And given such skew derivation of a ring, we can define a skew polynomial ring that is same as like polynomial ring. This is an free leptar module with basis 1x x square and so on. And but product is, here we have leptar module, so product with right by R will be defined in this way: skew by endomorphism tau and derivation this. And by universal mapping property, we can say that for given such endomorphism and derivation, we can exactly one such extension, that is actually skew polynomial ring. We can denote this as Rx tau and delta. And iterated skew polynomial ring is a skew polynomial ring whose base ring is also a skew polynomial ring. That is an iterated skew polynomial ring. But this skew polynomial ring has a nice properties. It's carry out some properties of its base ring. Here base ring is R. If R is domain and tau is injective, then this skew polynomial ring is will also be an domain. If R is prime ring and tau is an automorphism, then this skew polynomial ring will also be an prime ring. And next one is an important, that is gives us a Noetherian condition. If R is Noetherian and tau is an automorphism, then this extension is also a Noetherian. If it is left Noetherian, so extension is also skew polynomial ring is always a left Noetherian. We will use all these properties later for the example purpose. When we take an example of Q polynomial example of an quantum quantum algebra that can be present in skew polynomial ring presentations, and it is Noetherian or not follows from that properties actually. So now I will take, that is second part of my talk. Here I will consider two example of quantum algebra. First one is quantum affine space, that is just deformation of quantum polynomial algebra that we know. Quantum polynomial algebra is actually free algebra quotient by xy minus yx, like that if we take two variables, but here we take n variables. So here we have introduced lambda ij, where lambda ij are uh, some non-zero entries of the field actually satisfying some condition.
Why is
But
it
that,
called quantum affine space?
yes, because this the code, the commutative polynomial algebra, suppose kxy, that is actually coordinate ring of affine k2, coordinate ring of affine space actually. Here actually we have take affine space, but some non-existential object that is actually name as actually quantum affine space. That is actually quantum plane take that coordinate ring actually, and deformation the algebraic structure, then so this coordinate ring actually, that's deformation of that algebraic structure. That why quantum is come here actually. And we have considered here more general version, that is actually quantum affine space. First we have to define quantum plane actually, that is actually for two variable actually. And this quantum affine space is presentation is like that actually, k algebra generated by x1 x2 xn and satisfying some relation, and that lambda ij are non-zero entries of the field satisfying some condition. This condition is required to define that algebra well defined. And this algebra can be presented as an iterated skew polynomial ring of that form, twisted only by automorphism. There will be no derivation arise. And ordering of the indices is x1, x2, and xn. And here automorphism is looks like this. And by previous property of skew polynomial ring, as k is Noetherian and k is of course domain, and here all tau i's are automorphism. All tau i's are here automorphism because lambda ij are non-zero entries. So um, this quantum affine space is a Noetherian domain with some basis. K basis looks like this, and this K basis will follows from Diamond lemma. I am not going to that part, but exactly this will be the K basis as a vector space. That will be the basis. Next, we will actually show that quantum affine space is an PI ring under some restriction. Here the restriction is all the parameters are certain roots of unity. The lambda ij are roots of unity. If lambda ij are roots of unity, then quantum affine space will be a polynomial identity algebra or polynomial identity rings. That will be polynomial identity algebra, because if all lambda ij are roots of unity, then suppose some lambda ij to the power l will be 1, because there are finite number of ij. So x1 to the power l, x2 to the power l, xi to the power l will be such central element. So that that will be finite dimensional central simple algebra. Because of that k basis, we can say that this is finite dimensional central algebra. So this is a PID. And converse is also true. That follows from actually Kaplansky's theorem. I am not going to that part, but that is also true. If we suppose lambda 1 2 is not a roots of unity, then we take the algebra generated by x1 x2, and then we can show that this is not actually polynomial identity algebra.
Okay, well, if you take the polynomial ring, ordinary polynomial ring in
Yeah,
two variables,
yeah,
that is commutative. But if you take the twisted ring
yeah.
in like two variables, this
Mm,
quantum plane, right,
mm,
with Q not root of unity, why it
mm.
is not PI ring?
It is not a PI ring if not a root of unity. Suppose xy equals to qyx, q is not a root of unity. We localize with respect to the multiplicative set generated by x1 and x2, or xy generated by multiplicative set, and that will be a simple ring, and its center is actually k. So, and also primitive ring. So if it is pi ring, must be a center, must be infinite dimensional central simple algebra, but that will be the infinite dimensional algebra.
Okay.
I have not introduced all the proof there, but they are also important things. But my main target is to actually quantum affine space introduce and quantum Oil algebra. So now actually quantum affine space is um, actually prime because of domain, Noetherian prime and PI ring, and we assume now K is algebraically closed field. So we can use the previous result. So all simple modules are finite dimensional, and dimension is actually bounded above by its pi degree. Pi degree of its quantum affine space is we have to compute, but this is still unknown to us, so we have to compute that pi degree. But pi degree is actually here same as in terms of minimal degree, by it is minimal degree by 2. So now we will go to the computation of its pi degree. Suppose lambda ij be a roots of unity, so there are some finite number of lambda ij are there, so they are multiplicative subgroup of the of k star actually. So that is finite subgroup of k star that will be cyclic. Suppose q be the generator of that cyclic group generated by lambda ij, and m be the order, and then we can write lambda ij in terms of generators. So lambda ij will be q to the power hij, so hij will be entries from z, and that h will be denote the matrix hij, and that will be the skew symmetric integral matrix, because lambda ij are antisymmetric matrix. If you show the lambda ij properties of lambda ij, the power will be lambda ji will be lambda ij inverse, that will gives us h as a skew symmetric integral matrix. De Concini provides useful techniques for calculating pi degree for quantum affine space, which gives us, if in this way, suppose h be the cardinality of the image of the homomorphism induced by that skew symmetric integral matrix, that is n by n matrix, and zn to z mod mz power n, this is an homomorphism, and not an usual homomorphism induced by h. So this homomorphism it need not be a surjective always, because h is involved there. Okay, so suppose h be the cardinality of the image, then this cardinality will gives us about actually pi degree. So pi degree of that quantum affine space will be same as pi degree of that quantum torus, that is actually localization of quantum affine space with respect to the multiplicatively closed set generated by x1 x2 xn. This follows first equality follows from Poisson theorem actually, and the second equality follows from just mm, that quantum affine space is actually pre-module over its center actually, and rank is actually exactly that cardinality h, rank will be h, and
So you are not, when you are going from quantum affine space to quantum torus,
yes,
you are not
torus,
localizing at the low at central elements,
yes,
right?
yes.
So then how can you say that the pi degree will remain the same?
No, pi degree of quantum affine space and quantum torus is same because of that. That is because of Poisson theory. Because uh, pi degree of a quantum affine space is same as fact of pi degree of pi degree of quantum affine space, and this quantum torus lies between these, because this is just localization with respect to x1, x2, xn. If we
Yes.
take
Okay.
a central localization, that will be okay.
Yes.
I'm not going to the details of that proof of that De Concini result. That will be actually square root of h, and this follows from pi degree of quantum affine space. Is root h follows from the fact that a quantum affine space is finite module over it, center of rank will be h, and that can be easily compute that pi degree will be square root of h, because of same we have used Poisson theorem to get in central simple algebra. So for example purpose, we take a quantum plane that will be K algebra generated by two variable xy and with a relation xy minus qyx equals to 0. So lambda will be actually this 1q, q inverse q, and h will be this, because power of q actually h, integral matrix. So we can easily compute here the rank of h, sorry, cardinality of the image. We can easily compute the cardinality of the image and take its square root. If q is an primitive mth root of unity, then that cardinality will be m square actually. If we take ab here, then this will give us some b comma minus a return, and the possible value of b comma minus a or mod m will be m square possible. So that square root will be m. So if q is an primitive mth root of unity, pi degree will be just m. Now here actually one thing is the result of De Concini gives us that is cardinality of the image of that skew symmetric integral matrix. If we apply elementary operation, row or column operation on H, then the image will be same, because under elementary operation we add to row or multiply row by an unit element, like that. But in this operation the image will be same, so cardinality will of course same. But skew normal from which gives us a suitable form of an skew symmetric integral matrix, that change our skew symmetric integral matrix into a block diagonal matrix that will looks like this, where 2s will be the rank of H, rank of that skew symmetric integral matrix, and Hi divides Hi plus 1, and they are all non-zero, and they non-zero entries are called actually invariant factor of that integral matrix. And all H1 all Hi occur twice here actually. That is property of
So
skew
this
symmetric.
skew normal form, this is,
Yes,
this is the canonical form for,
canonical
what?
form for, you can say that canonical form for skew symmetric integral matrix actually, and that is special for
For
skew
which,
symmetric matrix, not for any matrix.
under, under which action means that, for example, Smith normal form is the canonical form for GLN cross GLN, right?
Yeah.
Because you can multiply by on the left and on the right.
Yes, here also multiply by left, and they are congruent actually. H
Huh?
is congruent to that block diagonal matrix.
Acha, so you mean that you are making your acting as P8 P transpose like that?
Yes, yes, absolutely, absolutely. So if we have a simpler form, rather than H, that's diagonal form, and from that diagonal form we'll easily compute the expression of pi degree in terms of invariant factor. That which looks like this. We will use later this actually to compute pi degree for more other algebras like quantum Oil algebra, and that's expression is nothing but just that will be actually order of H1, order of H2, and order of Hs actually. That's expression like m divided by GCD of Him in mod m actually, that is. So
So here you are assuming a cyclic, single, your quantum plane. You are assuming.
yes,
You are doing it,
quantum,
or
yes,
you are
we
doing
have
it for quantum n space.
quantum affine space.
So okay,
I have
m is the
calculated
order of
quantum for 2, that is usually I have calculated for n equals to 2. I have computed that is actually 2, actually am actually.
Acha, so this is your result, what you
No, no,
state in
no.
the
No, no, that is simply calculated, but I have seen that is appeared some thesis. I think some thesis there, but that is not much difficult to prove that. From this expression of diagonal expression to prove that pi degree is this, that is not much difficult. Just simply calculate suitably the manage the image actually. So now we come to the representation theory point of view actually. We want to find the representation of quantum affine space. So single parameter case is this case where lambda ij is q, only q, where I is less than j, and q is an primitive mth root of unity, we have assumed that, and then hij will be 1 for I greater than j. That means the capital H, the skew symmetric integral matrix, diagonal entries will be 0, and all the entries above the diagonal is 1, and all the entries below the diagonal is -1. And we can easily compute the rank of this matrix, and rank of this matrix will be n if n is even, and n minus 1 if n is odd. And all invariant factors are 1. If we compute easily, we, using suitable elementary row and column operation. So as all invariant factors are 1 and rank is also known to us, so we can say using this result that m to the power box n by 2 will be the pi degree, because box n by 2 is actually exactly box n by 2, 2 times box n by 2 is actually rank of that matrix actually H. And for representation,
float function.
no, box n by 2 is just greatest integer less than equals to n by 2. Here all the generator xi for the quantum affine space, that is normal element. Normal means they are Cauchy commuting in with all other generators actually. Cauchy commute means commute with some scalar actually. So as it is normal element, so either in any simple modules xi either acting like trivially or acting like invertibly. So each simple modules, take any simple modules on which xi acting like 0, then we can consider that simple module will be a simple modules with quantum affine space, smaller variables. So read same small number of variables. X square can be removed from there. So in this region, we can say it on its simple module xi acting like invertible or xi torsion free. So all xi torsion free simple module have been constructed and classified by Kanjumin and Sequano in his paper. And all these xi torsion free simple module are of maximal dimension. That dimension is actually m to the power box n by 2. That is actually pi degree. Maximal dimension is of course pi degree that I have actually uh, defined previously, and these simple modules are parameterized by some scalar parameters. Now recent times Snehasis with me, we are working on that algebra. Ashish sir proposed that algebra to work for multi-parameter version. For the multi-parameter version, just we have calculated pi degree, but that pi degree completely depends on that invariant factor, because invariant factor are cannot be computed explicitly in general lambda ij. So here just we set hi prime equals to gcd of hi and m. That is just a denominator. As h1 divides h2 divides hn, that invariant factors are divided. So hi primes also divides h2 primes and so on, hs primes, and hs primes also divides m. And we can explicitly say about h1 prime. H1 prime is will be always 1 because of the definition of an invariant factor, and as q is an primitive mx root of unity, or m is order of that cyclic group, that why h1 prime will be 1, and pi degree will just replace h1 prime because gcd of hi prime. So in this case we have classified simple module using the normal form of quantum torus. Actually quantum torus is actually obtained by localizing the quantum affine space with respect to the multiplicative set generated by x1 x2 xn, and its normal form is just this is rank n quantum torus. We say in literature it's rank n quantum torus where n appears, and its normal form says that it can be it will be isomorphic to an tensor product of rank 2 quantum torus and with an group algebra. And there are some rank 2 quantum torus will be depend on this all the parameters of that rank 2 quantum torus depend on h1 prime, h2 prime, and hs prime. And we have actually explicitly classified all xi torsion free simple module because it is enough to consider xi torsion free, because on other case we can reduce into an variable, reduce the variable of the algebra. So we have classified in all the simple modules in this case. Next, time is just over. Just here I will see one more things, not much details. That is quantum Oil algebra. Some things I want to say before stop the presentation. Quantum Oil algebra is another type of Oil algebra that is generated by two variable xy and with relation xy minus qy x minus 1, and if q is equals to 1, it will be the Oil algebra, and this is deformation of Oil algebra. That's why we introduce q here actually. And one more thing here I want to say that I have introduced previously as an polynomial identity algebra. Oil algebra is not an polynomial identity algebra for characteristic 0 because of it is a central simple algebra and infinite dimensional. Because of this reason, this is not an PI ring. And if we take characteristic 0 for Oil algebra, not quantum Oil algebra, if we take characteristic 0, then center will be bigger than Oil algebra, and all the representation for characteristic 0 Oil algebra are finite dimensional, and dimension will be actually exactly characteristic of the field. And now move to the quantum Oil algebra. Here just this algebra has a nice presentation in skew polynomial presentation, same as quantum affine space. And same, if q is a root of unity, then this algebra will be a polynomial identity ring. And pi degree, what will be the pi degree? Here is a derivation erasing process. I have not mentioned that, but this derivation erasing process will gives us that pi degree of an quantum Euler algebra is same as pi degree of an quantum plane, because of we remove that derivation from the algebra under certain restriction, but all the hypothesis is satisfied by quantum Euler algebra. We remove that derivation from the algebra, then this algebra will be becomes a quantum affine space. And if Q is a primitive MH2 unity, then this pi degree will be exactly M. Lot of thing I want to discuss today, but for time being I am not going to further. The main aim is just we are working on this algebra actually. This is for rank 1 quantum Euler algebra, that is known as for n equals to 1. In literature, there is no further progress or classification of simple modules greater than 1 actually. And for n equals to 1, all simple modules have been classified by Letzer and Wang. And all simple modules are measured most of the times m by m matrices actually. By they have computed by matrix solution of the equation xy minus qy is equals to 0. If q equals to 1 for Oil algebra, we know that this relation have no matrix solution. But if we take any q except than 1 and 0, then this is a matrix solution, and matrix solution will be the m by n matrix. But most of the time m by n matrix. If xy minus yx acting like non-zero, then the solution will be m by n matrix, and if xy minus yx acting like 0, then the solution will be one dimensional. And Soren Jandrov considered tensor product of this type of algebra, some m copies of tensor product of this type of algebra, and they have proved that there are m to the power s dimensional simple modules where s is lies between 0 to m and q is an primitive mth root of unity. And but they have not classified exactly these are the explicit form of simple modules. And I have mentioned that there is no further literature. More general version of Oil algebra exists in literature, that is multi-parameter version of Oil algebra. There is no representation is classified, and also pi degree is not classified explicitly. Here is actually pi degree is classified easily because it is tensor component. But we are working on this area with Snasis and guidance of Ashish sir. I have a result that I want to just state that, not prove that. Pi degree just multi-parameter quantum Oil algebra looks like this. This is the general framework of quantum Oil algebra defined by G. Malseniotis in non-commutative differential geometry. That is actually quantum Oil algebra. And some for particular version, all the previous quantum algebra will appear generated by 2n variables and this relation. Looking very absurd, but it has a nice presentation, skew polynomial presentation, all the things. And we can explicitly say under some restriction of parameters, qi is primitive LIX root of unity and lambda is here LIX root of unity. Under this restriction, we can say explicitly what will be the expression of pi degree. Just the pi degree, expression of pi degree will be product of Li. And we also classified some certain class of certain torsion free class of simple modules. Not all class of simple modules, certain torsion free class of simple modules. Zi torsion class of simple modules. So Zi is actually xi yi minus yi xi. If you see the definition of algebra, the Zi will be just xi yi minus yixi, not qi. That will be the Zi. All Zi torsion free class of simple module have been classified by us, Snasis, and we are working on this area for more progress actually. This is still open actually. Thank you. And these are the references, and this is thank you.
Yeah, thank you very much for your nice talk. Are there questions?
So you mentioned one remark that there is always a simple module, which
Yeah.
so suppose there is a prime algebra with pi degrees, some n, then there will be always a simple module which will have that PID, right? So
Yes,
what
yes.
is
I
the
have not mentioned that, but this is the actually scenario for oil algebra actually. For time being, I am not going to that details actually.
not
Here,
that mention that if you take an AC, any
for general prime PI algebra, you want to.
yes,
For general prime PI algebra, this bound is at n. I have mentioned here this bound is in fact at n, and for this at end of this bound, there is more theory because of that prime PI algebra will be a Jacobson ring, and we using this property, and also we define the notion of regulars prime. We can say that the all non-regulars primes are proper closed subspace of spec of R actually, and from that it follows actually. I have not details explicitly here, but this is attend actually, and this is existential one that is exist in literature actually.
okay.
Okay, thank you. Are there further questions? Okay, that seems not to be the case. Yeah, then let's thank the speaker again for a nice talk.
Thank you.
And next talk will be next week on Friday, and I will send out announcements soon. Okay, have a nice weekend.
Yes.
And I stop the recording and say bye-bye.